And I'll label these appropriately as Unit 1, Unit 2, Unit 3 review. So, okay, anyway, we're talking about work, energy, and momentum. This was stuff we did during week 3. Do you know these terms? Like kinetic energy, gravitational potential energy, conservation of mechanical energy, work energy theorem, conserved force, non-conserved, elastic and elastic collisions, impulse momentum, isolated systems, what is conserved. Make sure you know all those terms. If you do go to your notes, they're all right here. So we talked about non-conserved forces, and a bunch of stuff there. We also had discussed potential energy, conservative forces, so all that fun stuff. And even here we start defining what work was and work energy theorems. So make sure you know that. Now force and time are related to collisions and impulse. Force times time is impulse, so that's easy. Really force times a change in time is a change in momentum. Change in momentum is impulse. When is linear momentum and kinetic energy conserved? That's when we have a fully elastic, when they're both conserved. Other than that, then momentum is just conserved. You would need no external forces though, however. So if we do look at conservation momentum here, yeah, so the system has to be isolated. You don't want any other forces kind of acting on this stuff. And in order for there to be conservation of kinetic energy, in addition to conservation of momentum, then you need an elastic. But if it's inelastic, you still conserve the momentum. Now we actually get to some problems here, like 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so I like them all. Well, initially I do. Let's just make sure they're okay. And you can see they start the solution cube with number 4. So number 4, Mike's cutting grass. He pushes the mower with a force of 100 newtons directed at 20 degrees below the horizontal direction. So calculate the work that Mike does on the mower and pushing it 5 meters across the yard. Well, remember, here's your ground. Here's the lawnmower. Here's Mike. And he's kind of pushing like this. And we do have this 20-degree angle that we have to consider. So here's the actual force. And here's our angle, theta. But I want the force in the x direction. So cosine theta is a force in the x direction over force. So force in the x direction is force times cosine theta. And then to calculate the work he performs, you take the horizontal force and multiply by the distance. That's all you do. So that's why it's going to be 100 times cosine of 20 times 5. That's all. For 5, the kinetic energy is 7,000 joules. How much work is required to stop the car in 20 seconds? So you could think of this as, let me try to think about this here. I believe force over time. If you look at one of our formulas here. Looks like we don't have that. Yeah, but if we go back again, energy. Actually, hold on a sec. Okay, I'm losing my mind here. So yes, we don't know the mass of the car. Give me 1 second here. Actually, you probably would need the same amount of, yeah, I'm losing my mind here. Yeah, it's just gonna be the same amount of work, right? Who cares how long it takes? I was overanalyzing. I was thinking of, you have your initial velocity or acceleration. No, just, yeah, it's just you're stopping it. So if that's the energy you have, then you need to apply the same energy to get it stopped. So that's conceptual. I should have realized that. 6, a 15 kilogram block is lifted vertically 10 meters from the surface of the Earth. To 1 sigma, what is the change in gravitational potential energy? Just mgh, that's all you're doing. Very easy. For 7, an engineer's asked to design a playground slide such that the speed of child reaches the bottom does not exceed 4 meters per second. So that one, you're conserving energy. So your PE equals your KE. initially you have all P at the top of the slide. So it's mgh. And at the bottom side, it's all kinetic energy because now you're on the ground, 1/2 mv squared. Notice we're not given mass. It does not matter. You do not need the mass. G is 9.8. Height is 10. Sorry, it's not for the height. That's not for the previous problem. And 1/2, and your velocity is 4 squared. You just solve for h. So again, that could be a good multiple choice problem on the final. Keep moving here. Something like 8, a mass of 5 kilograms is dropped from a height of 1.4 meters from the ground. Okay. And onto a massive spring. The spring has an equilibrium length of 0.5. And when it crosses spring at 0.29, calculate spring constant. So the thing is that hold on, I'm actually a tad confused here where the ground is. I assume the ground is probably right here. I don't know why they do y equals 0. That seems a little weird to me. But I'm assuming that this is the entire that this is the ground straight up. And then obviously it hits it over here. Then it compresses it. So my guess is what you'd want to know. Well, we do know the force is just going to be mg of the rock. And then obviously there's a recoil. And it actually you have to look at how much it recoils. It recoils by 0.21. So a force of a spring is going to be negative kx. And the force, but it's actually going to be acting against the rock. The bottom line is that they have to balance each other out. The force of the rock, again, is 5 times 9.8. And you can say, you can keep it all positive, and k times 0.21. I'm pretty sure that's all they want. I think this is irrelevant because we're not dealing with energy so much. But let me double check a formula sheet here. I mean, there is a kinetic energy associated with springs, which is 1/2 kx squared. I wonder if that's what's happening with that one. Let's take a look at it really quickly. Yeah. So I kind of didn't think about this the right way. That's my bad. So I don't think I'll ask this one because we haven't done enough practice of this, especially because I'm not quite thinking about the right way. Yeah, that's not really quite right what I just did. So if we look at the solution key really quickly, it's just good to talk about the conservation, I guess, but the initial kinetic energy, of course, is just mgh, so duh. And then there is a final potential energy because it's still 0.21 off the ground. And you have 1/2 kx squared, and you solve k in that fashion. So yeah, I probably should have realized that, but I won't ask that on the final. Don't worry about it. 9, warehouse work used a forklift to lift the crate. 5 meters combined mass of the platform is that. The power, how long does it take to lift the crate? Remember, power is actually going to be work over time. So we have that formula right here. So you should be able to kind of figure that out. I'm not going to work it out for you guys. I'll let you work through that one. But you do have the mass. You should be able to get the weight. And then you also have the distance. You should also be able to get the, you should be able to choose energy actually. So you should be able to do MGH to get the energy and then divide by time equals the power. Pretend Jennifer's walking that speed, just weighs that much. From her weight, you should be able to get her mass and multiplies the velocity to get the momentum. For 11, 10 kilogram steel balls drop straight down a hard horizontal form, bounces straight up. Its speed just before and after impact is that. Determine the magnitude of the impulse. So you should be able to, yeah, so that's gonna be the change in velocity. So obviously it has initial speed of 0. Just before and after impact. Okay, let you guys work through that one. 12, yeah, you should be able to do conservation momentum there. Likewise at 13. And then slams the brakes. Yeah, you're going to be doing a conservation of energy in this case here. And you have a non-conservative energy, which is, or non-conservative work, which is the friction. So anyway, I'll have you guys do 4 through 14. I kind of already worked through some of these, but I'll give you guys about 20 minutes so to kind of work through these problems. We'll meet again, see if you have any questions, and we'll wrap it up for today. So put you guys back in your breakout rooms. Stop the